Good morning, everyone.
Good morning, sir. Sir, we'll wait just for a few minutes, then we'll start.
Yeah,
The participants are joining. हम्म हाँ हो जाने देते हैं फिर कर देंगे।
so is there a feedback from the students? Am I going too fast? Am I going too slow? Is it boring?
It is actually very good session. They are appreciating in chat box, so you can also see that excellent session they are saying. So there is no problem, anything like that actually, and no one has said anything like that. So yeah,
That means people are not understanding.
no sir, actually they are. That's why they are asking so many questions. So and participants are also sir means always at about 100 or more than that. So sessions are very good actually, sir.
Okay.
Yes, sir.
Someone is saying we don't get sleep, Nitin Sharma. Thank you.
Yes, sir. Mm. So now we can start, sir. I think
Okay.
most of them have joined. So good morning, all the participants. Good morning, sir. So welcome to the third day of short-term training program on Introduction to Seismic Analysis and Design of Structures. Today, sir is going to deliver lecture on response spectrum method of analysis. Welcome, sir, and now you may start, sir.
Okay. So let us start the session on response spectrum method of analysis. I hope you can see.
Yes, sir.
Okay. So here in this lecture we will discuss what is response spectrum, and how do we generate these response spectrum, then how do we use this response spectrum in the design method. So yesterday there were some questions on how to, not how to, but the calculation of natural period of vibration in the seismic analysis. Someone asked, like, do we need to calculate it manually, or it will be automatically calculated by the software? So some of these features we will discuss in more detail today. Uh, the better title for this lecture would have been seismic analysis of structures, right? Because response spectrum is one of the methods of seismic analysis. But why I chose this topic? Because it is the most popular method of analysis in our IS code. Our IS code recommends this method for slightly complex structures. For very simple structures, small structures, not very high, there is another method that we'll also discuss today. It's slightly modified version of response spectrum. But this is very interesting method, and especially the development part, how this response spectrum is developed. That is really interesting. I hope you will understand the way we need to do the calculations. Uh, all of you know what is a ground acceleration. So whenever there is an earthquake, the ground vibrates, and what we measure during this earthquake shaking is the acceleration, ground acceleration, as a function of time. So if you look at this figure here, uh, the x-axis here is time, time instance in seconds, and the y-axis is acceleration. Now in this case, the acceleration is given in 500 centimeter per second square. Okay. Now, if you want to understand how much is the velocity, how much was the velocity during the earthquake ground shaking, how much was the displacement of the ground, then it is possible that you can actually use this record and convert it into a velocity time history, and then you convert the velocity time history to the displacement time history. So this is the real ground motion recorded during 1999 Taiwan earthquake, which has had a magnitude of 7.6. So you can see here it is written that the maximum acceleration recorded during this event by this station, by this instrument only, is 500 centimeter per second square. Okay. Now that means during that earthquake, that single instrument, the maximum acceleration recorded was this, right? So it is about 0.5 meter per second square. Now we generally do not understand what is this 500 centimeter per second square is. I mean, how big or how small is this? So 0.5 meter per second square. We don't have much understanding on that. But as soon as I say that it is 0.05 g, right, or 0.1 g, then you have a very good understanding that okay, so this is the acceleration as a function of g value, gravitational acceleration. So 0.5 meter per second square is about, you can say 5% of g, 9.8 meter per second square, right? So when I say it in terms of g, then we have a very good understanding. So therefore, in most cases, we refer to this acceleration in terms of g, acceleration due to gravity. Okay. So similarly, we can derive this velocity time history from this acceleration time history. There are simple methods available for that. We will discuss some of those methods here. So this is the real number that was available, that is available for Taiwan earthquake, and displacement time history is this, and you can see here that the maximum displacement that was recorded is 742 centimeters. So this is about 0.75 meters of displacement. Now this is the permanent displacement of the ground, right? And generally it happens near the faults, not very far away from the fault. So there are many instances, many earthquakes where such permanent deformation of the ground is occurred. Okay, so we can use any one of these and we can obtain another. So There is no additional information given by any of these records, any of these time histories. Okay, and we call them time history because they give historical information with respect to time, what happened at that instant, and how long the earthquake was, what is the frequency, what is the duration. So several terms are here, but the point is we can convert them from one to another. But we can also record them. We have instruments that can record velocity as well as displacement. The acceleration records, they are unique for every earthquake. So they are the signatures of that particular earthquake. We cannot have exactly same kind of earthquake recorded for two different earthquakes. It's not possible because of many issues. Because of primarily the ground is different, the frequencies are different, frequencies of the waves, the type, the energy that these waves carry, that is different. The type of instrument, the foundation of that instrument, is it located on rock or what type of soil, how deep is the rock, so many factors are there. Therefore the each recording is actually a signature, right? So here I am showing you so many records, typical accelerographs. Now these records are known as accelerographs, and the instruments that record it is known as accelerograph or seismometers. Okay, so though the name of the instrument is such that it appears to be a graph, right? But the graph is actually accelerographs. Accelerograph is an instrument. Now, this El Centro earthquake that occurred in 1940 is very famous. In almost all research, people use this earthquake to validate, to check the structure, whether it is safe or not. It has several reasons. One is this El Centro is basically the first earthquake recording, proper earthquake recording in the history where we had so many records in different directions. So here it is shown as 00E. So this is the identification of this earthquake record. It shows the directions of the instrument, but sometimes you will also find the name of the station where the recording was done. So the another reason that people use this earthquake very frequently in their research is it has so many frequency content, so much of frequency content that it is when we analyze the structures using this, it is expected that the structure will respond. In a very vigorous manner in the sense that the response will be higher. So we can check the structure for safety here easily. So you can see here there are several earthquakes. This Parkfield earthquake, absolutely different from this. This is a small earthquake in 1970. San Francisco earthquake, Fernando earthquake, such large earthquake, but the duration is less here. And this is the Chile earthquake of 1985. This is one of the largest earthquakes ever recorded on the surface of the earth. You can see how long the earthquake duration was here. And this is a Northridge earthquake, another benchmark earthquake that has created so much of damage in the bridges in US, the Loma Prieta. And this Mexico City earthquake that we discussed yesterday. So this was recorded on that SCT site, if you remember that, right? The filled up lake site. And see here the axis is given, the y-axis is the acceleration in terms of g, right? So it is all the values of acceleration are divided by acceleration due to gravity, and that is how you can actually compare these because all of them have similar scale. Okay, now one thing is very important here: acceleration recorded by each of these by these instruments in different earthquakes. So that is a maximum value, maybe on the negative side or on the positive side. So that maximum value of the ground motion record of the accelerogram is called the peak ground acceleration, and it has a very important role in seismic design. We'll discuss that. Now let us start with the response spectrum. So yesterday I told you that this has two words. One is response. So obviously we are talking about response of the structure, and the second word is spectrum. So that means it covers a lot of numbers, it covers a lot of points, a lot of range. So it shows you entire spectrum of the response. So if I have to define it, it can be defined as it's the maximum response of a single degree of freedom system for a given natural period and damping. So two issues are here. First, you need to have the natural period of that system, single degree of freedom system, and second, we must have damping of the system. Okay. Now, development or generation of this response spectrum is not very difficult. It is actually very simple. If you can solve the equation of motion, you can very easily do this. And there are many programs available freely on internet which can actually develop response spectrum for any ground motion. So the method is very simple. You have to consider any ground motion for which you are planning to develop or generate the response spectrum. So consider any ground motion. For example, this ground motion I have considered where the peak ground acceleration PGA is about 0.32 g. So you can see here this number. This is, I think, or maybe this number somewhere is the peak ground acceleration, right? So I will take this earthquake. The second thing required is the natural period of vibration. The third thing is the damping. So then I will consider a single degree of freedom system. The time period of this system will be 2 pi under root m by k. So I need mass and I need k, which is stiffness. So if I can get mass and stiffness, I can get the natural period of vibration. Okay. And then I need the damping value for which I want to develop the spectrum. Now how do we get different values for T? It's simple, you just keep on changing the mass and the stiffness. So as soon as you change the mass, time period will be different, so you have another structure. You change the mass again and you have another structure. So that is shown here. So consider the ground motion time history, find out what is the maximum displacement or what is the displacement history of this single degree of freedom system. So this is what is plotted here. So obviously if I take this single degree of freedom system, apply this ground motion at the bottom of this single degree of freedom system, it will vibrate, right? And if I can measure that vibration in terms of displacement, let us say the displacement of this mass, so I can plot it. So for every instance, I will get this displacement, right? So it is also called displacement time history or time history of deformation response. So I will get the relative displacement of this mass with respect to the base, right? So that I can plot here. Now you can ask, how will I get the maximum displacement here? Because, or forget about maximum, how will I get the displacement at every instance of time? Right? Because it is not done experimentally. It is theoretical calculations. So the answer is very simple. You know the equation of motion of the single degree of freedom system subjected to the base excitation, right? So mx double dot plus cx dot plus kx is equal to minus mg double dot. You just solve that equation for x. Okay, x is the relative displacement between the mass and the base. So you solve it. There are methods available. You can very easily solve that. I mean, you can have a computer program that can give you the solution for X. You actually need a computer program to develop the response spectrum. Manually, it is not possible to generate the spectrum for hundreds of points. 1 or 2 points you can do, but not the entire spectrum. So that is how you plot this displacement history. Now, from this displacement history, you just take one point, which is delta 1 max, the maximum value of that. So that gives you the maximum response of this single degree of freedom system when subjected to this ground motion. Okay, so that is one point. Now you change the property of the system such that you get the natural period of 1 second. Again repeat the process, so you get another point, just one point, which is the maximum displacement from this displacement time history. Here in this case it is 5.97 inch. Third case, you change the time, the natural characteristics again, maybe mass, maybe stiffness, natural period will change. For that natural period, you subject, for that single degree of freedom system, you again apply the ground motion at the base and you get the displacement time history. Here, the delta 3 max for this structure is 7.47. Now you can see the difference in the behavior of the structure, the difference in the displacement time history. So when the period was very less, 0.5 seconds, its frequency is very high here. So you can see the response. The response frequency is also very high, right? When you increase the time period, you can see the change in the behavior. Okay, for very flexible structures, time natural period of vibration of 2 seconds, you see how low the frequency is here of the vibration. Okay, so that means when the structure is there, and I hope you understand what is the meaning of natural period of vibration. So if the structure is standing like this, it will go in this direction, half cycle, it will come back to original position, it will go on the negative side and then come back to the original position. So this much this structure is covering in 2 seconds. Now you can imagine high-rise structures, they have to vibrate it like this in 2 seconds. 0.5, the same thing, it has to do in 0.5. So this is very high frequency, the low frequency that is very easily visible in case of the third figure. Okay, so after doing so much of analysis, so much of uh, uh, solving the equation of motion so many times, we get only 3 points: delta 1 max, delta 2 max, and delta 3 max. Right? Now, what I will do, I will try to plot that displacement, maximum displacement on the y axis versus the natural period of the structure of the single degree of freedom system. So, this is my first point, delta 1 max. This is my second point, delta 2 max, and delta 3 max. So on and so forth. So I'll do this hundreds of times, thousands of times to get this entire curve, to get the entire spectrum. So if I want to have a more gradual, a more, not turn like this, sudden drop, I need to have more number of points here, right? So thousands of points if I can have, I can actually make it more smooth. So that is what is required to be done, right? So do these hundreds of analysis, thousands of analysis and plot this. This will give you the displacement response spectrum of single degree of freedom systems with different natural period of vibration and only one value of damping, that is zeta 1. Okay. Now if you want to change the damping, you have to again redo all those calculations by considering different values of damping. So 5%, 10%, 7%, right? So that is the variation in that same displacement response spectrum. So that is what is shown. So remember, this is the maximum response only. We are not worried about how much is the displacement response at any particular instance, but for that structure, what is the maximum displacement? So one structure is actually represented by one natural period of vibration. Okay, so that is how we generate response spectrum. And this is a very common MTech project given to students in any IITs. I'm sure in different places also, in other engineering institutes also, to generate the response spectrum for single degree of freedom system. So now, like we did for displacement, we can also generate the response spectrum for velocity. So those will be called the velocity response spectrum and the acceleration response spectrum. So the method remains the same. Instead of displacement, you have to find out the velocity and the acceleration. Now, it is not necessary to do all these calculations again. Once you do the calculations for displacement, once you have that solution ready with you, you don't have to do another, don't have to find out another solution for velocity and acceleration. For that purpose, we can actually do something else. So the responses are maximum relative displacement. So we plot it SD versus T, spectral displacement versus time period. Maximum relative velocity. So we plot spectral velocity versus time period. Maximum absolute acceleration. So that is in relation to the ground, right? With respect to ground. That is spectral acceleration versus T. So these are the three response spectrum that we can plot. Okay. Now, instead of having spectral velocity versus t and spectral acceleration versus t, we can simplify the process. So we can use pseudo responses, because otherwise we have to calculate the response of the structure in terms of velocity and acceleration also. So people generally do not do that. We approximately calculate what is this velocity spectrum by multiplying the spectral displacement for which we have the solution with us. So we can multiply the spectral displacement with the term omega, that is the natural frequency, and get omega SD versus T. Now we will discuss later in the next slides why we call it pseudo velocity and why we call it pseudo acceleration. Right. So if you look at our design acceleration, it is actually PSA, pseudo spectral acceleration, pseudo spectral velocity. Okay, so these are not the real velocity and acceleration, but these are derived responses. And the reason why we use derived responses is simple, because once you have spectral displacement, you can simply convert it into pseudo spectral velocity and pseudo spectral acceleration. Let us see what is this pseudo thing. So if I consider a single degree of freedom system again, so here is that system. The whole mass is lumped here, so it is having only a single mass that can vibrate only in one way. So that is why it is called single degree of freedom system. The base shear, I hope you remember what is base shear. So base shear for this single degree of freedom system is VB, and I'm putting T here to just let you know that I'm talking about just an instant of time. So for that instant, this is the base shear. Now at that instant, the lateral force acting on that mass is Fs of T, right? So from equilibrium, we can very easily say that the VBT is actually Fs of T, right? So base shear is equal to this because there is only one mass here. If there are multiple masses, we will discuss how to distribute this base shear to multiple masses. But here, single degree of freedom system, we have this equilibrium. Now, what is this Fs? This is a force. Now, we can very easily compute this force for this single degree of freedom system by multiplying this displacement of the mass with the stiffness provided by this columns. Okay, so stiffness times displacement is what? It's a force, right? It's the stiffening force. So this Fs we can write in terms of K times Ut. Again, Ut is the displacement response at that instant here of that mass, right? If I ask you what is the definition of stiffness, everyone will reply that it is the force required to apply unit deformation, right? So this is the same thing. So stiffness is basically Fs divided by U, the force required for unit displacement. So we use the same equation, same fundamentals to write down this equation. So force is stiffness times displacement. So this stiffness K is actually the lateral stiffness of this single degree of freedom system provided by these columns. Now, I hope you remember what's the stiffness of a cantilever column. If you consider that there is only one column here and it's a cantilever, we apply load in this direction. The stiffness of this column, I hope all of you remember. So that is why that is how it is done. For a frame, you can again calculate depending on the behavior. So then I'll come back here. F of Fst is K times U. Now, if you remember the formula for calculation of natural frequency, omega n, that is, omega n is what? Under root of K by M. So if I replace this K with M omega n square, so omega is basically K by M, so I'm replacing K by K with M omega n square here, right? Otherwise, this is the same equation. So we can write it. Now you also know the Newton's law of motion, which says that force is actually mass times acceleration. So mass is here, and obviously this term has to be some sort of acceleration, right? So we write it as m times at. So this at is basically what? Omega n square times ut. Okay, so this is called pseudo acceleration. Right, so this is not the real acceleration, but this is a derived acceleration from ut. Ut is nothing but sd, the spectral displacement. So that is how we actually can very easily find, instead of using spectral acceleration, we can very easily use this approximated quantity, which is pseudo spectral acceleration. And I hope you will remember it from where it came. It is very simple, only from equilibrium, and we simply substitute stiffness with this m omega n square, and that gives you this. Now, what is the base shear then? So base shear, if you remember yesterday's lecture also, it is basically some factor, that is the lateral force coefficient or base shear coefficient multiplied by W, right? So base shear, uh, I mean from this equation, mass times, sorry, this A is omega n square ut, right? Now we can replace this mass with W by G, right? So that is the same thing done here. So this equation we are converting to this equation. So A multiplied by W by G. So G we bring here, and this A by G becomes the base shear coefficient. So this is the yesterday's equation again, that magic equation we discussed, where we multiply that coefficient with the weight, seismic weight of the structure. So this is the derivation of that equation. I hope it is clear. Even if it is not clear now, you can just go through this slide again, and I'm sure it is very simple. You can remember that. So this is the base shear coefficient or lateral force coefficient used by the building codes to represent the coefficient, right? So like I discussed yesterday, any structure has to be designed for some percentage of its own seismic weight, right? So this A by G represent that uh, uh, ratio for which we have to actually design the structure. Okay, so this is the basics of all those things. Now, so that is how we are actually plotting here the velocity response spectra. Now this is the spectral velocity, not the pseudo spectral velocity, but we can even plot it. So this is for El Centro earthquake. This x-axis is the natural period of vibration, y-axis is the maximum velocity. Okay, so you can see the values for different the spectra for different values of damping here. So obviously when you increase the damping, the response reduces. So that is what is shown here. But see how the curves are, how the spectra are here. It is not as gradual, as smooth given in our IS 1893. And the reason for this is the response spectrum for just one ground motion, right? Developed for a limited number of points, limited number of structures. But if you find out the average response spectrum developed for hundreds of ground motions, then you can actually smoothen it out, just like the design response spectrum given in the code. And this is the acceleration response spectrum that you can develop. So like I said, here is the spectral acceleration. So this is the actual acceleration that you have to actually derive from the ground motion directly. Okay, not the derived acceleration, not the acceleration derived from the spectral displacement, but directly from the acceleration records. So here also you can see these are different, not different damping, but for different earthquakes. And you can see here how these spectra, they change the shape. This is very interesting in the sense, and remember x-axis is always the natural period of vibration of the structure. It has nothing to do with the ground motion, right? Y-axis is spectral acceleration or spectral velocity or spectral displacement or pseudo-spectral acceleration or pseudo-spectral velocity for that structure again. Again, it has nothing to do with this acceleration. Acceleration has already given the energy to the structure, and this is the maximum response of the structure. Remember, it has nothing to do now with the ground motion. It is the response of the structure. So the interesting point here is to remember is the response spectrum has a typical shape. Now see what is the value of this response, the spectral acceleration at zero time period. Can you see here? Is it reaching zero? So what I am asking, at zero natural period of vibration, is the spectral acceleration zero? It is not, but it starts somewhere here, right? And it depends on different ground motions. What will be this value? So if you remember the peak ground acceleration, so this value actually is the peak ground acceleration. At natural period zero, this value will directly start from the peak ground acceleration. And the reason we'll discuss later. Why is it so? Some of you already been knowing it. And then what happens? Initially, when we increase the natural period of vibration of the structure, that means when what do you mean by zero period structure? When the natural period of vibration of the structure is zero, that means the structure is infinitely rigid, right? So it is moving along with the ground. It has no relative motion. So the structure is rigid, right? So it moves along with the ground. So what happens? The whatever is the ground acceleration, the same acceleration will be transferred to the mass. Exactly same thing. So if you remember, on the y-axis, we plot the maximum response only. So what will be the maximum response of the ground motion for rigid structure? It will be obviously the peak ground acceleration, right? So that is why at t is equal to 0, you always get that peak ground acceleration here, right? Now when you impart some flexibility to this system from rigid to slightly flexible, then you see what happens. The response of the structure increases, right? So this is interesting. It increases up to a point only. After that, you will find that it tries to balance for some time, right? So this is the region where you don't have much change in the response, but after this region, the response reduces. So this is the interesting thing here. In almost all response spectrum, you will find it will increase initially for a small amount, for a small natural period, and then remains more or less constant, and then it reduces. It is very simple to understand because when you impart some flexibility to the system, the relative motion suddenly increases, right? So this mass, it starts vibrating vigorously, and obviously the because of the amplification of the ground motion from base to top, the 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 acceleration of this mass will be more than the peak ground acceleration. Okay, so that is why initially you have higher acceleration response, and when the natural period of the vibration of structure increases, obviously the structure will actually start vibrating with less frequency, with less vigorosity. So you will have lesser acceleration when you increase the natural period because it becomes flexible. Flexibility means the displacement will increase, but then the acceleration will reduce because it is not vibrating. When it vibrates more vigorously, then the acceleration is more. But with increasing time period, the acceleration reduces. So that is what is shown here. So this is very simple to understand why it increases initially, because there is some flexibility introduced in the system. Because of it vibrates. Otherwise, initially it was rigid, and after some time, after imparting more flexibility, the response reduces. Now, unless otherwise mentioned, the response spectrum is based on linear elastic system. Okay, but then we can also develop the response spectrum for inelastic system, and we will do this today. What are the uses of the response spectrum? Obviously, the first use is to obtain the maximum response of a single degree of freedom system. Now we already know that y-axis, it represents a maximum response, right? So if you have a system, you can calculate the natural period. Obviously, immediately you can calculate what is the maximum acceleration or velocity or displacement for this structure. But for the single degree of freedom structure, so if you plot that response spectrum for a particular accelerogram for just one earthquake, so this maximum response will be corresponding to that earthquake only. But if you develop an average response spectrum considering hundreds and thousands of ground motions, you can then say that this is the average maximum response of the structure. Second is to obtain maximum response in a particular mode of vibration. Now, whenever we develop this response spectrum, we say single degree of freedom system. But then in reality, there is no single degree of freedom system. The buildings, all everything is actually multi-degree of freedom system. So how do we use it? And we use the response spectrum given in the code, always to design. So we use it by converting these multi-degree of freedom systems into combination of several single degree of freedom systems. And for individual single degree of freedom systems, we can obtain the maximum response in that particular mode of vibration. Okay, and then somehow we club this, we add these modes of vibrations of different modes of the multi-degree of freedom system to get the response. To understand the characteristics of the ground motion, So response spectrum actually also gives you some characteristics of ground motion. For example, peak ground acceleration. Right. So looking at the response spectrum, you can tell this is the peak ground acceleration. Then how was the acceleration in the sense that what is the plateau? I will discuss this later when we discuss the design response spectrum. So how much is the plateau? How much is the amplification from zero time period to a time period up to which it increases? So these are the things we can check. Now this is one simple example of how to calculate the maximum base shear for a single degree of freedom system, and then on the basis of that how to calculate the maximum base moment. So this is the system given to you. It's a single degree of freedom system having mass lumped at the top, and the value of this mass is 10 tons, right? So it is 10,000 kg. The natural period of vibration of this structure of this system is 1 second. Damping is given as 5% of the critical, right? If I don't give you this natural period directly, I can give you the height of this system, and I can give you the section properties of this system. So from the cantilever behavior, you can find out what is the stiffness, right? So for example, cantilever, the stiffness is 3EI by L cube. You know E, if I give you the material, concrete, so you know E, I have to specify the grade of concrete. If I give you the section properties, you can calculate the moment of inertia. So EI by L cube, L you already know. So from there you get stiffness, and 2 pi under root n by k will give you the natural period of vibration. So you know all these things. What we need to do is to find out the design base shear or the maximum base shear. So what we will do, we will construct, and I need to find out that maximum base shear for this ground motion. This ground motion is also given to me. So first I will develop the acceleration response spectrum for this ground motion using the method given. So this is the acceleration response spectrum I have already developed for 5% damping. You can see here that at natural period 0, it starts from about 0.35, roughly 0.32, 0.33 G. Look at this response, look at the ground motion here. What is the peak ground acceleration? How much is the peak value? I think this is lesser than this peak value. So this is slightly more than 0.3, right? So this exactly same point is shown here. So about 0.32, right? And then it increases, almost remains same, and then it reduces. Now I want to know how much is the response, maximum acceleration response of this system. So what I'll do, I'll go back to this 1.0 natural period, and then this is the value. This value is about 0.48, right? So the spectral acceleration for 1 second is 0.48 g. That is how we use the response spectrum. Now you know that if you want to find out the force, it can be calculated as mass times this acceleration. So maximum base shear at the base of the structure can be found out from mass, which is 10,000 kg multiplied by the spectral acceleration, which is 0.48 times 9.81 meter per second square. Okay, so remember here you are using kg. So when you use this kg and m by the what is weight is basically m by g. So the force that you will get is in terms of Newton. But if you are using this mass in terms of tons, then you will get the force in terms of kilonewton. Okay, so simply multiplication of this will give you 47,000 Newton of the base shear. So that is the maximum base shear occurring at the bottom of that structure, right? Remember, the maximum base shear cannot be given by the peak ground acceleration. The peak ground acceleration was only 0.35, 0.32, right? But the spectral acceleration for this structure was much more than that 0.32. Okay, it is 0.48. So that is why you cannot use this. You cannot use this to compute the maximum response. Now you know the maximum base shear. There is only one mass, so the force acting at that mass is also similar. So you can find out also the maximum base shear, base moment, by simply multiplying this 47 with the height. So this is the values of the maximum base shear and the moment. And this is how we use it. The basic reason of showing you this simple thing is, don't assume that this peak ground acceleration will always give you the maximum value, maximum response. It will never give you. And you can imagine from starting from here to here. So for all these structures lying in this zone, the response of the structure, maximum response of the structure will be more than the peak ground acceleration, right? Only for these structures, the response will be less than the peak ground acceleration. So now how to smoothen these response spectrum? So we have seen the real spectrum, they are irregular, they are local peaks and valleys. So we ignore these peaks and valleys, we try to smooth them by having large number of points, by having large number of count motions, and then doing averaging. Even after doing that, we are not able to actually regularize the shape. So in that case, we actually ignore some of the peaks and ignore some of the valleys just to have a smoothened or average response spectrum. Now, the reason why we ignore is that if you consider this response spectrum, let us say, and the natural period of vibration of the structure is about 0.25, maybe 0.22 seconds. So in that case, which value of acceleration will you consider? Will you consider this or will you consider this? So these are lying so close to each other that it is very difficult. So if you consider this, you may underestimate. If you consider this, you may unnecessarily overestimate. So it is better actually to ignore some of these points, and I would rather use some average curve. That is why we ignore some of these points. So these are some of the smoothened response spectra, and you can see the acceleration spectra, the velocity spectra, and the displacement spectra for different damping values. You can see it starts from this peak ground acceleration, but here the peak ground acceleration is 1 because it is normalized with respect to the PG. Okay, all these curves. So it is normalized here. So this value will always be equal to 1. In case of IS 1893 also you will find such value. It starts from 1. Velocity spectra, obviously when the natural period is 0, the relative velocity is 0. When the natural period is 0, the relative displacement is also 0, so it starts from 0. But then when the time period is 0, the acceleration is not 0. That is the absolute acceleration of the structure. It is not 0. It is vibrating. It is accelerating exactly with the same acceleration that is of the ground. Okay. This we have already discussed, that peak ground acceleration is the maximum acceleration of the ground. But then when you show this on the response spectrum, and if there is a structure with 0 natural period, that becomes also the peak acceleration of the structure. This is again a definition that seismologists use. Instead of uh, rigid structures, they call a 0 period acceleration. I mean, it's not a time period, the TA value of 0, same thing, but they imply that the maximum acceleration experienced by structure having 0 natural period. So like I said, it is infinitely rigid. So ZPA is a term defined by seismologists. It is exactly same as peak ground acceleration. For very low values of period, they say that acceleration spectrum tends to be equal to PGA. Now, don't be confused. In our code also, there is a slightly different definition of 0 period acceleration. There is a small change, but not for engineers. Don't worry about it. The average shape of acceleration response spectrum for 5% damping. Now we will see the next slide. What is the change in the shape of the spectrum? Again, there is another definition which is effective peak ground acceleration. See, these are the terms developed by seismologists to define several regions in the response spectrum. So this effective PGA, EPGA is defined as 0.4 times the spectral acceleration in this zone, 0.1 second to 0.3 second range. Okay, and you will understand in next slides what is the use that this EPGA has. But then let us not worry about it much as engineers. So this is the typical shape of response, acceleration response spectrum, right? So this is spectral acceleration, it starts from zero point 0.6. So this is PGA, it increases initially and then more or less remains constant for some time and then reduces. Okay, now the point is this region from here to here, what is the time? What is the time? What is the difference in the time period? So the normally this is between zero point 0.1 and 0.3 seconds. This from here to here, so up to 0.1 seconds it increases, and between zero point 0.1 and 0.3 seconds it more or less remains constant, and after 0.3 seconds it starts reducing. Now between this zone 0.1 and 0.3 seconds, the value of acceleration, spectral acceleration, is about 2.5 times the peak ground acceleration. Okay, for 5% damping. So these are some of the approximations that we do when we use the design spectrum. So let us see what is that design spectrum. Basically, if we are using the spectrum given in the code for design purposes, then we have to use a very smooth and response spectrum. So the seismic design force can be calculated from the design response spectrum. Okay, but if you are using a response spectrum developed from a particular ground motion, that will not be the design force. That gives you only the maximum force for that ground motion. Okay, now you already know the seismic design philosophy, that some damage is expected in the structure during strong shaking. So design spectrum is developed considering the overstrength, considering the redundancy, and considering the ductility in the structure. So now you can imagine what all goes into developing the design spectrum. Why it has to be regular, it has to be smoothened. So the design spectrum must be accompanied by load factors or the permissible stresses. It must be accompanied by damping that is used in the design, because obviously the damping value will affect the design force. The method of calculation of natural period, it has to be specified, and the type of detailing for ductility must be specified. So all these values must accompany a design spectrum. Otherwise, if I simply give you a design spectrum without any method to calculate R or I or SA by G or Z, it is of no use actually. So whenever you have a design spectrum, you must have all these quantities. Now here again, if you remember yesterday, the spectrum or the response of that of the structures located in Mexico during Mexico City earthquake, it depended hugely on the type of soil. So obviously the response spectrum will also depend on the type of soil on which the structure is located. So here we have tried actually to develop the response spectrum of the same structure and same earthquake, but located on different soils. So you can see for the soft soil, the response is maximum. The response is more for these structures. And as we go on increasing the stiffness of the soil, so this is for the rock, the response is less. But it is actually less after a particular time period. Before that, for very short period structures, the response will be more in case of rock. And if you remember the first lecture where I discussed the performance of structures during past earthquakes, we discussed something called the ridge effect. So the structures located on the top of the hill, they are vibrating more, they vibrate more during earthquakes. So that is called ridge top effect. And this is actually reflected here. If you have rocky strata and low natural period of vibration, you have higher response. But for most of other structures, for softer soils, the response is low. Now it is very obvious why the response should be more, because the the structure is actually free to vibrate on the softer soil. The soil is so soft that it does not provide much rigidity at the base. The structure vibrates more vigorously. Now this is the elastic design spectrum. This is not the design spectrum of our IS code, but this is how the design spectrum looks like. So It is there for different values of damping. So this is for 1% damping, 2%, 5%, 10%, and 20%. So look at the shape. Just like I said previously, that 0 at t is equal to 0, you have peak ground acceleration. It is 1 because normalized with PGA, and it increases up to about zero point 0.1 seconds here, right? More or less zero point 0.1 second. From 0.1 to 0.3, it more or less remains same. This is the plateau I was talking about. So how much will be this plateau depends on the type of ground motion, and then it reduces from here. Now this is for a particular soil only. If I change the type of soil, the response spectrum will also change. Now these are the design response spectrum given in the code. Up to 2002, we used to have only one type of design response spectrum, which is this. But from this 2016 version, there is a slight change in the design response spectrum if you use equivalent static method. Now, why is it so? We will discuss. But now you have two distinct types of design response spectrum. One, if you use equivalent static method, another if you use response spectrum method. Okay. So these are the three curves for three different soil types. So softer soil obviously will have higher response. Rocky soil will have low response, but only in this zone. Before that, the response is more or less same. But we have seen response of structures located on rocky soil is more, but then we don't do that here. We normalize the response. Here you see the design response spectrum starts from 1 because again it is normalized. Now, when you take this value here, it is SA by G, so spectral acceleration divided by G value. You have to multiply it with Z by 2, then you multiply it with I by R, right? So all those terms, when you multiply, finally you multiply it with the seismic weight of the structure. Then it gives you the base shear. So that is why it is actually normalized. It starts from 1 because you have to multiply with several other quantities to do the final calculations. Now let me explain why this part is removed from the recent code. Now there are some structural designers, structural engineers which are very clever. Just in order to reduce the design forces, what they do, they calculate the natural period in this zone. They will say that my structure has a natural period of 0.05 seconds or 0.02 seconds. It is so rigid. So if that is so, the design force will reduce. But then the codal committee recognize this, that people are doing this. So they say that okay, if you are using response spectrum method, then it is okay. But if you are using the equivalent static method, which uses the natural period formula given by the codes, in that case you cannot reduce that response. So the response is actually maximum response here is 2.5. You cannot further reduce it, whatever is your time period, right? So that is why. Now we will discuss further when we discuss the response spectrum method, the advantages of doing that. So yesterday somebody asked me like how to find out which type of soil is it. So there's a table 4 given in the code. Depending on the SPT values, depending on N values, you can actually find out what type of soil is it. And it is very straightforward. I'm not going into detail. Everything is written there. So the effect of the design earthquake loads we can consider using two methods. So first is the equivalent static method. So the code say that for regular structures that have natural period of vibration of less than 0.4 seconds, let us say, you can use it. These are very simple regular structures. But the dynamic analysis method is actually recommended for any irregular structure, for all structures, even with natural period less than 0.4 seconds, even if there is some irregularity. So the response spectrum method is one such dynamic analysis method. Along with response spectrum, the code also recommends doing modal time history analysis or time history analysis methods. Depending on the irregularity, the code also say you have to use a nonlinear analysis. Now, so these are the three methods adopted by the IS 1890. Equivalent static method, response spectrum method, and time history method. So we discussed when do we use it, but then we have not discussed what are the changes. I think in one of the answers to the questions asked by one participant yesterday, I explained this that if it is a very simple structure, you can analyze that structure manually in the sense that you know the seismic weight of the structure, you know what is the importance of the structure, importance factor, what is R value, what is Z, everything you know. You can similarly you can find out what is the natural period of vibration using the equations given in the code. From there, you use the design response spectrum and get SA by G manually, and then you calculate the base shear. So this is equivalent static method. So natural period is calculated using the equations given in the code. But if the structure is slightly complex and it is not possible to actually divide the multi-degree of freedom system into several single degree of freedom system manually, then we use the computer's help to do that. And that is called the response spectrum method. So in this method, we don't use the natural periodic formula given by the code, but we allow the software to do the modal analysis and calculate the natural periods of vibration for different modes. So for every mode, for that natural period, modal period, the software computes the maximum response SA by G from the design spectrum which is given as input to the software. So let us say there are 10 modes of vibration, it will compute 10 SA by G values, find out the base shear, and then it somehow it combines all these responses of single degree of freedom system to get the final response. This is the response spectrum method. Now again someone asked this question yesterday, like what are these reduction in the gross moment of inertia? So this recent version of the code, it says that for seismic analysis, structural analysis, the moment of inertia can be reduced. So for RC and masonry structures, the moment of inertia of columns can be reduced to about 70%, and for beams, it is about 35% of the gross moment of inertia. So if it's a rectangular section, the moment of inertia is BD cube by 12. But because of some micro cracks, because of several movements, because of environmental factors, there is always some damage in the reinforced concrete members. Always, even before subjected to any loading. So because of that minor micro cracks, that damage, the stiffness of this beam, stiffness of these members, it reduces. And the reduction is very high. It can be 30% reduction to 65% reduction. That is why the code say that there is no need to unnecessarily consider the gross moment of inertia. You can reduce the moment of inertia. Now, what happens when you reduce the moment of inertia? The structure becomes more flexible, right? So 3 EI by LQ is the stiffness of the cantilever, right? Uh, so if you reduce this I value, what happens? The stiffness value will reduce. So when the stiffness reduces, what happens to the natural period? 2 pi under root m by k. Natural period will increase. So when the natural period increases, you somehow make the structure flexible and the design forces are reduced. So that is why the code says that there is some chance that your structure is slightly flexible compared to the gross stiffness, and you can reduce the design forces. But for steel structures, there is no such thing, and we have to consider the gross I for both beams and columns. So these are the design response spectra values given in the code for rocky strata, for medium stiff soils, and for soft soils. So you can see this is for equivalent static method, and this is for the response spectrum method. So you can see here that for less than 0.1 second, the SA by G is given by this. For time period between 0.1 and 0.4 seconds, SA by G is constant, which is 2.5. Between 0.4 and 4 seconds, it varies as the inverse of t, and beyond 4 seconds, you can consider this constant as 0.25. Okay, and for different soils, this is more or less same, but the only change is here. The time period during which that plateau can be considered. So it increases with the soil, with the flexibility in the soil. So for soft soils, the plateau goes further beyond. And this is the vertical seismic acceleration. Yesterday again someone asked how to consider that. So these are given in the code. So for buildings that is governed by this IS 193 part 1, you can consider the vertical acceleration coefficient spectral value to be 2/3 of this value, z by 2, I by r, and instead of SA by G, the code say you simply consider the maximum value, which is 2.5. So this is how you do it. And for other types of structures also, the code has given the numbers. For liquid retaining tanks, for bridges, industrial structures. And this is of course SA by G is to be calculated based on T here in this case, natural period. Now there is another interesting way by which we represent the response of the structure. These are called tripartite plots. Now if you remember, I said that this acceleration, the velocity and displacement, they give same information, right? There is no additional information given by any of these. So the response spectrum for acceleration, for velocity and displacement also give you exactly same information, because you can derive the other from one. So we can very easily show all these responses in a single chart. So this is what is shown here. Here you can show the spectral acceleration, a spectral displacement and spectral velocity all in one. So it is called tripartite plots because all three are there. It is also called combined displacement velocity acceleration spectra, combined DVA spectra. And since we also are interested in the natural period, because without natural period we cannot find out the response, the scale is a four-way log scale. Okay, let us see where are these four axes. So this is the tripartite plot of the response spectrum from this earthquake of 1989 in Loma Prieta. Okay, this is the natural period of the structure, right, on the x-axis. Now you can see this is a log scale. Okay, so 0.1, 0.2, 0.5, 1, 2, 3, 5, 10. So up to 10 seconds it shows. So this is a log scale. This axis here, the red axis, is the spectral acceleration axis, right? This axis, the blue axis, is the spectral displacement axis. And this vertical axis here is the spectral velocity axis. Okay. Now all the four axes are plotted in the log scale. Right, so it's very easy to see here that everything is in log, in terms of log here. So if you plot the response spectrum, it will look something like this. Only single curve, but it will give you the values of spectral acceleration, spectral velocity, and spectral displacement, everything. Now, how do we calculate it? So let us say that this is SA axis. So when you move along this SA axis, you are changing the values along XD axis. Okay. So when you are moving this way, SD changes, right? So SD values are given here. So for example, this value, this is SD, is 0.1 centimeter, right? So this axis, it represents 0.1 SD. This will be 0.2 SD, 0.3 SD, this will be 1 SD, this is 2 SD, 3 SD, so on and so forth. Right, so this is 3 centimeter, this is 1 centimeter, this is 10 centimeters, 100 centimeters. Similarly, if you move along this, in this direction, along the SA axis, this axis represents 0.01 G. Right, so this is 0.02, this will be 0.1 G, this will be 1 G, this will be 10 G. Okay, and similarly, this is SV axis. So this value is 0.2 centimeter per second, and so on and so forth. So for any time period, let us say 0.5 second, I want to know how much is acceleration, velocity, and displacement of the structures, maximum values. So I come here, right? So very easily I will tell you that this is more than 100 spectral velocity for 0.5 seconds. The value of acceleration will be this, somewhere this. So I have to count down from bottom to here, and the value of displacement will be this, corresponding to this axis. So this is the advantage of using tripartite plot. Now these are the special cases. Like I already said that for zero damping values, this is not discussed, but like I already said that we can actually derive pseudo-spectral acceleration from spectral acceleration. But these values are not exactly same. These are derived values. But for zero damping, the spectral acceleration is exactly same as the pseudo-spectral acceleration. But even for zero damping, the spectral velocity is not exactly same as pseudo-spectral velocity. That is because of the energy, we don't know the exact energy that is supplied to the system. Let us not discuss this issue in more detail because we will have to spend some more time on that, but I am not inclined to discuss that. But what is interesting is for small damping values, spectral acceleration is more or less equal to PSA. Spectral velocity is also more or less equal to PSA. Now, small damping means what? The 5% damping is considered as small, right? So, even for 5-7% damping, we can consider this as very good assumption. For rigid system, the spectral acceleration we already know is the peak ground acceleration, right? So, for low damping, the pseudo spectral acceleration is more or less equal to peak ground acceleration. Now, what happens with the infinitely flexible system? The spectral displacement becomes the peak ground displacement, right? So whatever is the ground displacement, if there is a system which is infinitely flexible, very high natural period of vibration, so whatever is the ground displacement, the same displacement will be there on the structure. The spectral velocity is again equal to spectral pseudo-spectral velocity, but the spectral acceleration now is zero, and that you can see here also. If I show you this response spectrum, so for very high natural period, the spectral acceleration goes on reducing, right? And for infinitely large values of t, we can say that the spectral acceleration is zero. For same system, the pseudo-spectral velocity is omega n times sd, which is equal to zero because the frequency is zero, right? So that is how we compute it, and pseudo-spectral acceleration is because it is omega n square times sd, it is actually equal to 0. Okay, now even for zero damping, like I said, these values are not equal. So just remember that whatever we are doing is simply the assumption. Now let us see what is inelastic design spectrum and how do we derive it, how do we develop it. So what I am showing here is this curve is an elastic design spectrum. Okay, we have developed it in all these slides, we have actually discussed it. But then you know that the system is ductile, so in real sense, if you're not using that R value, then you cannot use that design response spectrum. We can use that design response spectrum because R is there in that magic equation. Let us say there is no R there. Let us say there is no consideration of ductility in the design response spectrum given in the code. So in that case, you have to develop your own ductility, your own inelastic response spectrum or different ductility values. Now, when you increase the ductility, you know that the response will reduce. The maximum force, maximum response, acceleration response is going to reduce, but the displacement response will increase. So this is what is done here for different values of ductility. So for any structure, you can see that the value, the response reduces. So this is called constant ductility design spectrum because the ductility is constant for this entire spectrum. It is the constant ductility response spectrum. We can also plot it in the tripartite plot, right? The four-way log plot like we have done before for the elastic spectrum. Now this is how we do it. The process is simple. We have to consider the elastic design spectrum first. We have to develop it, and then we reduce it. We divide the elastic response spectrum by a factor Ry, right? So this factor actually represents the ductility of the system. So this is ductility reduction factor. So this factor is given here. So for natural period less than TA values, there is no reduction. For natural period between TB and TC prime, the reduction is under root 2 mu minus 1. And for natural period more than TC, the reduction is by ductility. Now let us see what does it mean. So these points here A, B, C, D are given here. So this is point A or A prime, which correspond to 1 by 33 seconds. So very stiff structures, very low values. Okay. This point is B, which correspond to 1 by 8 second. So this is the natural period of vibration. Remember, this is point C, point D. This is point E corresponding to 10 seconds, and point F corresponding to 33 seconds. This elastic design spectrum you already have developed, right? Now, this is again the tripartite plot. Now, what you have to do, you have to divide this by different values of Ry in different regions, different zones. For example, if the time period of the structure is less than Ta, now this is A. So for less than this, there is no reduction because of ductility. It is same curve. Between B and C prime, so this is point B and this is point C prime. So between this zone, you have to reduce it using under root 2 mu minus 1. So this A here is reduced, is divided by this term, right? So you get this line up to this point. This you already know. So this point you have divided up, you have reduced up to this point. So you can join these two lines, these 2 points. This point you have divided here, again join these two. And it says beyond C, you use this mu factor. So here, you keep on dividing every point by mu. So that gives you the inelastic design response spectrum for that particular value of mu, for that particular value of ductility. It is simple, just some calculations. Now, there is another way we can actually represent the response spectrum. It is called acceleration displacement response spectrum, ADRS. So here what we do, on y-axis we plot the acceleration response, acceleration spectrum, and on the x-axis we plot the maximum displacement response. There is no axis for time period here. So when we do this, when we plot it, we can actually plot the diagonal lines, and the diagonal lines in the sense lines crossing origin. So with different inclinations, if we draw each of these lines, they represent some natural period of vibration. Okay, so for example, this line here, it represents the natural period of vibration of 2 seconds. This line here represents 5 seconds. This is for 1 second. And you can plot this ADRS curve for different values of ductility, for different values of damping. It is exactly same curve, again giving you exactly same numbers, but the difference is that we can use this curve, ADRS curve, in nonlinear pushover analysis to compute the performance point. Those of you who are doing this, they will be knowing what is performance point. Otherwise, anyway, we are going to discuss in the last class. Now, why these inclined lines give you the natural period of vibration? The answer is simple. What is the slope of this line? The slope of this line will be AY by D. Now, this pseudo-spectral acceleration is omega n square times spectral displacement divided by spectral displacement. So, you get omega n square directly. So, from that omega n square, you can find out what is the natural period of vibration. So, this is the ratio of these two terms that gives you the natural period directly. So, this is the advantage of using these types of curves. Now, let us come to the actual analysis, the lateral load analysis, for which we actually started this lecture. But I thought without discussing the basics, it's not useful how to do the calculations. The calculations are very simple if you understand all these basics. So, These are all the basic design philosophy that we have already discussed in the first class. This is the magic equation that we have already discussed, all these parameters. So let us move forward and try to use it now. So you know that the design seismic base shear can be calculated from this AH by multiplying it with seismic weight. Okay, and how to calculate AH? So AH is a function of seismic zone factor. It's a function of SA by G, which in turns is a factor of natural period of vibration and damping, factor of importance factor, and the response reduction factor. So everything together gives you AH. I hope now you understand what is there inbuilt in the design response spectrum given in the code. So all these factors are taken care of, right? So if any of these factors is removed, then you have to actually develop your own response spectrum. We will discuss this issue later. When are we required to develop our own response spectrum? This is again repetition of the type of soil. I will not discuss here. So for equivalent static method of analysis, the code has given us several formula to compute the natural period. So these are some of the details given in the code. I will not go into detail here because it's very self-explaining. You can understand it by just reading it. So just note that we have different natural period now in this present standard for reinforced concrete, for composite, and for steel buildings. Previously, it was not there. And the code also gives you, methodology to compute the height of the structure. Because yesterday also someone asked, like, what is the real height? So the code gives you some help here, how to compute the height. This is the second equation for buildings with the structural walls, and the another equation given for all other buildings, right? So this is the similar equation that was there previously in the code. Now I am assuming that you know about this equation because it is very simple. If I tell you about just this equation, it is a function of length of the wall, height of the wall, and area of the wall. That's all. So you can very easily compute all these terms. Not difficult. Okay, so in equivalent static method, we compute the design base shear for the building as a whole, and then we distribute this VB to different floors. We will discuss how do we do that. Uh, the Once we distribute the design force to different levels, the next step is to distribute this force at a level to different units of that floor, and meaning different columns, different walls. That can be done if you know what is the lateral stiffness of these systems. Now this is very important that this method is applicable only for regular buildings with height less than 15 meters in seismic zone 2. That's all. So congratulations to all who are in Jabalpur, and if your building is less than, let's say, 5-story high, then you can use the simplified method. Otherwise, no. So only in seismic zone 2 you can use it. But then this is such an interesting method that people use it every time because it gives you the flavor of the design force. So response spectrum method, which utilizes the software cell, sometimes we commit some mistakes in the software, but then if you know about the structure from this method, you have some confidence of the minimum design rules. So that is why people always use it. So this is the seismic zone factor, you all know. This is the response reduction factor that we have already discussed, and these are the different values of the response reduction factor given in the code for different structures. Okay, the maximum value is 5 for the special moment resisting frames. These are the important factors for different types. Now in this report, there is an additional factor defined, which is okay. Previously it was only 1 and 1.5. Now this point is interesting. In seismic analysis, the code gives you one advantage. And it says that in seismic analysis, if you are using seismic analysis, if you are doing seismic analysis, Then you have to consider full dead load, but you can reduce the live loads. You can reduce the imposed loads. So the reduction is very large. If the live load is less than 3 kilonewton per meter square, you have to consider only 30% of the live load. If the live load is more than 3 kilonewton per meter square, you can consider 50%. And why is it so? The reason is again very simple, that earthquakes do not occur frequently and the live load may not be there fully when the earthquake struck. For example, a classroom. So in a classroom, the duration of the classes is maximum 8 hours per day. It's only 1/3 of the time, right? And even during that 8 hours, it's possible that full live load may not be there. So the code allows you to consider less loads. Now you can imagine, when you consider less imposed loads, you are reducing the seismic weight of the building. And when you reduce the seismic weight, AH into W will reduce, so the base shear will reduce, so the design forces will reduce. So this is allowed by the code. But the code also has a very interesting feature in the new version. It gives you the minimum design lateral force for different zones. So it says that the code says that you do whatever type of analysis, linear, non-linear, response spectrum, any type of analysis, but then your design force, your design base shear should not be less than this number given here, right? So these are these percentage numbers given. So this is, if your structure is in seismic zone 5, you cannot design your structure, any structure, for less than 2.4% of the seismic weight. Okay, so this is the value given in the code. So you do whatever, but the minimum design force will always be 2.4% of this W value. This is the same thing that I just spoke. Now, how to distribute the design base shear VB to different floors? So this is the equation given in the code. So it distributes the force to different levels in parabolic manner. So Wi is the weight of the ith floor, Hi is the height of the ith floor, and same thing here. So this is the design base shear. So you distribute it using this equation to different floors, right? And here we assume that the floors are have that rigidity in their own plane. So the distribution is possible because of that. But if the floor is flexible, we cannot do this. For example, if the floors are wooden, then it's actually difficult to distribute this. So for that, we have to carry out some specialized analysis by considering in-plane flexibility of the diaphragm. Now, once you calculate these forces at different floors, so this combination of this will be VB. If you add them, you get VB. Next step is you distribute this Q1 to different members here, right? So there may be shear wall, there may be these lateral force resisting elements. You can distribute them, each of them. So there are, let us say, there are n number of frames. So Q1 is at a particular level, but there may be 10 frames in the other direction. So this Q1 at a level has to be distributed to 10 frames. Now that distribution is done using the relative stiffness of these frames. Okay. So there is another interesting thing in the code. It says that if you calculate the design base shear using dynamic analysis and you calculate the design base shear, which is VB bar, using the empirical natural period, this VB, which is calculated using dynamic analysis, should not be less than VB bar. If it is so, if somehow you can manage in your dynamic analysis, if you have done something to your model and you manage to reduce the design forces such that the design forces given by the seismic coefficient method are more, then that is not permitted. So the code says that you increase the design forces by this ratio. Simple. So again, if you remember that table, it gives you the minimum design force. modes. You cannot go below that. Now, in response spectrum method, people will ask like how many modes to consider. Like I said, you can actually consider several single degree of freedom systems, each corresponding to the natural modes of vibration. So how many modes to consider? If you have a software, then you don't have to worry about it. You can consider hundreds of modes. But it is seen that those hundreds of modes are not important. So what you have to see is that you have to consider those many modes in which at least 90% of the total seismic mass is considered. So only that is required. So that is what is shown here. So 90% of the mass should be accounted for in the model. Now you have this, converted MD of system into several single degree of freedom systems. You have found out the design forces for individual single degree of freedom systems, how to combine them. So there are some modal combination rules given in the code. So one is the CQC method, complete quadratic combination. Those of you who are more interested in this, they can read the literature, but then if you're using a software, it is automatically done there in the software. Then next is the square root of sum of squares, SRSS method. So these are different methods. Another is simple absolute sum. You just club everything, you just add everything. Now you cannot use any of these methods for anything. There are requirements that, for example, this SRSS can be used if the modes are very well separated. That means if the frequencies differ from each other by 10% or more, only then you can use it, in the sense that this will give you better results. The most softwares, they use this CQC method. It's there already inbuilt. But if you are doing manual calculations in your classes, SRSS is more preferred because it is more easy. Load combinations, you have to consider all these load combinations given in the code. There are 13 load combinations for unsymmetric buildings, considering dead load, live load, earthquake loads. Now remember, this load case, dead load plus live load is there, right? So in this load case, you cannot reduce the live load, okay, because there is no consideration of earthquake load here. But when you consider this load case, in which the earthquake load case is there, you can reduce the live load to 30% or 50%, if you remember that table, right? So wherever you have earthquake load along with the live load, you can reduce the live load. And most important point here is the code say that you can even consider zero live load at the roof of the structure. In this combination, if you are doing the earthquake load combination, you can reduce the live load at the roof to zero, and you can reduce the live load at different levels to 30 or 50%. Now, in some cases, you have buildings which have non-parallel force resisting systems. So in this case, the question is which direction loading you have to consider. So if you consider x direction, you get this forces ELX, earthquake load x direction, and this earthquake load y direction. But then there are certain members which will not be critically designed if you consider this ELX or ELY. So in that case, we use another load combination for non-parallel systems. It is called 130 loads. What do we do here? That in one case, so we analyze for ELX, we analyze for ELY separately, and then we add them. So ELX plus 0.3 ELY and 0.3 ELX plus ELY. So that is what we do. We add them by 130 to calculate the design force for these members only. So this is what we do for the 2 or 3 component motion. So same thing, ELX plus minus ELX plus minus 0.3 ELY plus minus 0.3 ELZ. So this is what we do. Or we can also use the SRSS here. So square root of sum of squares. That is also permissible. And we have to consider the
Hello, sir.
Yes.
Sir, why we are considering this 130? Why not some other value, means 140 or 50? Is there
Yes, there is a simple derivation for this. we can discuss maybe in some other class, but if you do this 130 rule, then you are actually approaching approximately to the real design force in this memory.
Okay, sir.
There is no need to consider zero point 0.4 or zero point 0.5. That actually is overestimating.
Okay, okay, sir.
This is sufficient for this. Maybe we can discuss later. Maybe I don't remember where you there in my class. I generally teach this in my class.
Yeah, I watched, sir, but long back. So yeah, maybe I'll check notes. Yes, sir. Okay.
Yes, yes. So that is a derivation. There is a derivation for this. We can
Okay.
actually do that.
Okay.
Now, the last point is site-specific design criteria. So, like I said, in some cases, you have to develop your own design response spectrum, your own response spectrum. The reason is, let us say you want to design a dam, you want to construct a dam. So, for that dam, it is recommended that you don't use the response spectrum given in the code, because the response spectrum in the code is the average response spectrum. So, but you have to consider, you have to take into account the local geology, local seismicity, local geotechnical conditions, the nature of the project before you can design the dam. Similarly for nuclear power plants, similarly for bridges also. So in those cases, you have to develop your own site-specific response spectrum by considering the past seismicity, by looking for the ground motions that were experienced in that region in the past. Right, so there are many references, you can read it, but this is a general practice that we develop our own response spectrum. Now remember, when we develop your own response spectrum, there is no question of considering R there, right? Because this is not the design response spectrum of IS 1893. The design response spectrum of IS 1893 has inbuilt values of this R, this I, this Z. So therefore, because it is normalized, so therefore you have to actually use all those factors along with the design response spectrum. But if you're developing your own response spectrum for the ground motion, for that soil, you don't have to worry about all these factors. This will give you the site specific criteria. So thank you very much. If you have questions, we can discuss.
Thank you, sir. Participants, you may ask your questions. Actually, you can't type your questions in chat box. You just ask, sir. He will explain everything. So unmute yourself and ask.
Hello, sir.
Yes.
Okay. I have one doubt. So you said that when time period is very high, that is the structure is flexible, it has more displacement and less acceleration. So
Yes.
my question is, what is preferable? So the structure should have less acceleration and more displacement, or vice versa? What will cause less damage?
See, you have to have a good balance between two. If you remember yesterday's lecture, see, if you have very flexible structure, in that case, am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Yeah, if you have a very flexible structure, of course you can reduce the acceleration, but then the displacement will be so huge that there will be problems related to non-structural design. There are several pipelines, there are electrical fittings, there are so many things in a building other than the structure, right? So there will be huge problem with that. Plus, if you have been to, I mean, super high-rise structures, that is a 100-story building, and if you are staying in a 100th floor of that building, you will realize that even during normal winds, you actually move and you can actually feel that movement. And if you're not accustomed to it, it is very inconvenient. Right? So what people do in very high-rise structures, very super high-rise structures, they have additional features to reduce this displacement. So the idea of designing a very flexible structure is good, but then unless you have that control, you will face other problems. So therefore, there have to be a proper balance between these two. So we can design the structure for a particular force, obviously, but then we have to accommodate the displacement also.
Okay. Thank you, sir. So there are lots of questions in chat box. I don't know why people are not unmuting and asking.
Mr. Vaibhav, you just unmute yourself and ask your question. You have posted 3-4 questions, I think. So you just unmute and ask.
Hello.
Yes.
Good afternoon, sir.
Yeah.
Sir, my first question is about the stiffness modifier for slabs. In the 1893 code, we do not have a stiffness modifier for slabs, but in the tall building code, they have specified it. So, why is that so?
See, tall buildings, the behavior, the performance is completely different. You see, so let us say you have a reinforced concrete slab in a 4-story, 5-story building. Now, when we design these buildings, we assume the rigidity of these slabs in their own plane. So that is called flexion. That is called the rigid diaphragm. Okay. Now, if the diaphragm is rigid, if the floors are considered as rigid, then how does it matter whether I am reducing the gross moment of inertia of that slab or not? Because we are already considering it as a rigid member. We are not finding out the design forces for that slab using this response spectrum method. The design for slabs are different. But in in the tall building code, they have actually considered it because of various other issues. Because in some cases you have flexible flat slabs. So it says that if you are actually finding out those forces, if you are modeling them properly, then the design is different. But in simplified normal buildings, it is not required.
Okay, sir. Sir, another thing I want to ask is about the live load reduction factor as per IS 875. Do we
Yes.
have to consider it?
Yes, of course. Whatever is written in the code, you have to consider it. And
Even
reason I have already told you why do you need to consider it? Because if you consider, then your design forces will reduce. So it is beneficial.
Sir, I have written a design combination in the chat box. Can you confirm this?
Design combination.
Yes. As per your slide, you have said that we can reduce the live load depending on the condition.
So what you have written is 1.2 times dead load plus 0.25 LL plus ES. Yes, this is now one thing here is don't increase it's up to you actually whether you really want to multiply this 1.2 with 0.25 LL. Okay, so on one hand you are reducing the live load to 25%, but on the other hand you are again increasing by 20%. So this is one problem in the code. You don't have to do that, right? So this 1.2 factor is applicable for dead load. You may not apply it for live load, but it is applicable for earthquake load.
Okay, sir. Thank you.
Yeah.
Good afternoon, sir. I have a query.
Yes. Good afternoon.
Sir, how is the parabolic distribution of base shear arrived in equivalent static method?
If you remember that equation is there that distributes the base shear to different levels.
Yes, sir. Yes, sir.
So that equation is parabolic equation. That's a nonlinear equation because it gives you the seismic. It is a function of seismic weight and height. So WH square divided by summation of this WHI square.
Sir,
So yes.
is it because in the first mode, the shape is the deflection is something like in a parabola? So,
No, this is only for the individual mode, right? I mean, you cannot simply say that the first mode is always parabolic,
okay, sir.
right? So for simplicity, the code says that this is the way you can actually distribute the base shear to different levels. Now the question is, do we distribute using a straight line, or do we distribute using a different cubic parabola, I mean, a cubic curve or a parabolic curve? So what people say that if it is a parabolic curve, then you get more critical responses.
Okay, sir.
So it has nothing to do with the real distribution. Right? Real distribution will be different, but this is the design code.
Okay, sir. Thank you.
Mr. Prashant, you may ask your question now.
हेलो सर, गुड आफ्टरनून, आई एम प्रशांत।
हाय प्रशांत।
सर मुझे पूछना था, जैसे हम लोग स्टैड में एनालिसिस करते हैं, सो जैसे जोन 4 का अगर मैंने एनालिसिस जोन 4 या जोन 5 में एनालिसिस किया तो कॉलम का जो थिकनेस आता है उसमें वो मिनिमम 300 पे जैसे अगर पास हो रहा है, देन हम लोग अगर उसमें बीम का जो एनालिसिस करते हैं उसका जो थिकनेस होता है वो 230 mm का में वो हो जाता है पास। तो वैसा अगर प्रैक्टिकली उसमें क्या होता है, मतलब प्रैक्टिकली वो ऑफसेट दिखेगा वो तो हमेशा ही, तो उस केसेस में क्या करते हैं?
तो ऑफसेट दिखने में कुछ दिक्कत है?
सर मतलब और प्रैक्टिकली वो अच्छा नहीं लगेगा, ऐसा एस्थेटिक ऐसा कुछ रहता है?
ऑफसेट वर्ड से ही
हाँ
भारत में कबाड़ा हो रखा है।
जी।
क्यों? ये जो 9 इंच के कॉलम बनते हैं वो क्यों बनते हैं?
वो वॉल के कारण।
वॉल के कारण, क्योंकि वो हमारे घर के अंदर ऑफसेट अच्छा नहीं दिखता है। हमको क्यों नहीं दिखता है भाई साहब? आप ऑफसेट दिखाइए, कॉलम बड़े रखिए, वॉल छोटा रखिए। तो ऑफसेट की चिंता ना करो।
ओके सर।
No need to worry about this offset, but worry about the structure. Let
Okay.
there be offset, no problem.
Okay. Okay sir, thank you.
I think this was the last question, sir. Thank you very much, sir, for the session, and we'll see you in next session, sir.
Yeah, thank you. Thank you all.
Thank you very much, sir. Thank you.